to talk about tailored waveforms, a bit different, different focus than maybe Scott's small version to this. But he talked about how it influences ionization mechanisms and flux uniformity. I'm going to talk about more how it affects ion energy. And we don't have the kind of just TCP plasma, but actually ICPs with tailored waveform biasing. And it's actually the project that James actually mentioned shortly during his talk. And why do you actually want to do this? It's because these tailored waveforms promise to give you much better control over ion energy than your conventional sinusoidal waveforms is the short answer. And this is actually specifically interesting for atomic layer etching, which Scott already explained nicely. So thanks for that. But maybe just to reiterate, in the end, what you want to do with atomic layer etching is you want to etch a material one monolayer at a time. How do you do this? You put in some gas, usually called precursor, which modifies the upper layer of your surface, usually with the goal to lower the bonding energy. You purge it, then you put in a plasma, and you have ions on the surface, which then should only remove this upper layer, but not the underlying material. Then you repeat this. So this really gives you an etching one monolayer in each cycle. However, in order for this to work, you really need precise control over your ion energy. But as I said, you only want to etch the upper layer, which the lower bonding energy, but not what is beneath. And usually these bonding energies are roughly in the 10 eV range. They are usually not too far away. So in the end, if you want your material A on the surface, material B, you really want all your ions to have energies between these two bonding energies. Because otherwise, if it's too low, you don't etch anything. If it's too high, you etch both the monolayer you want to etch, but also what's beneath, and you don't want that. So you really need to get IEDFs, which maybe cover a few tenths of eV at most. Perfect would actually be completely monoenergetic IEDFs. And as for example, Mark has already shown, you don't get this with your conventional sinusoidal waveforms. There you get, due to the transient electric fields in the sheet, you get these bimodal IEDFs. And how much this spread depends on frequency, ion mass. So if you have a sufficiently high frequency and sufficiently heavy ions, you might get very close to a monogenetic IEDF, but in general, you get these bimodals, depending on frequency, depending on ions. You might maybe say, okay, I tune it, so that's this high energy peak is in this window you get, but again, then you kind of waste half your ions because half the ions don't do anything because they have too low energy. And of course, you have to consider, since it depends on the ion mass, if you have not just an argon plasma, but multiple gases or molecular gases, you have different ions, all different masses, which have all their individual IEDFs. So you get a large spread of ion energies, which you don't want for your ALE process. Obvious solution would be using DC voltages. However, this only works for if you have a conductive surface, which wafers typically aren't. Otherwise, these in a DC discharge, this wafer charge up, you get a voltage drop over the wafer, and the electric field actually does not penetrate into the plasma, and you don't accelerate your ions. So these don't seem. For practical applications, DC voltage simply don't work. And this is where these tailored waveforms come in. Typically, what are used, the waveforms which are used to get these kind of nearly monogenetic ion distribution functions. You see there, basically you have a very short positive phase to attract electrons, and then a long negative phase to accelerate the ions. Now, one thing you have to consider is electrons only reach the surface during the short positive phase. So over this long positive phase, only ions reach the surface. So they still get some transient charging during this negative phase, and which is why you then introduce this slope in the negative phase to counter the charging of this wafer, but also of the blocking capacitor in your network. And typically, people always talk about DC self-bias. But in the end, it's not actually a DC self-bias. It has transient components, but typically, if you are in megahertz range, these are small compared to your complete DC self-bias. But that is not the case. For example, might not be the case if you're at frequencies of hundreds of kilohertz or so. And in these cases, you typically actually have transient behavior of the DC self-bias over this RF period. So you also need to compensate for this. So you need to compensate for both the charging of the wafer and the charging of the blocking capacitor. And experimentally, it has been shown that you can actually get this nearly monogetic IEDFs. So we thought that, well, let's try to simulate this. We did it kind of as a side project. So whenever I, or sometimes also Young had some time or was just waiting for some simulations to finish, we kind of played around with these waveforms a bit, just looked, well, what happens if we apply different shaped waveforms? Can we get there? Worked quite well, but at some point we kind of hit the limit because we didn't get enough information on, for example, how do these waveforms actually look like? When you buy a generator, you can buy generators which do this. How do these actually look like? How do the IDFs get? So we kind of hit a block there. So we teamed up with Oxford Instruments, applied for a grant, didn't get it. I think we missed the threshold by 1%. A bit less than 1%. But apparently some weeks later they took pity on us and gave us the money anyway. So we actually had this kind of 6-month grant where we worked together with Oxford Instruments. They did the experiments, we did the simulations, and see how close can we actually get in the simulation to the experiment, and maybe what other things can we learn from the simulation. And yeah, James has already mentioned this. One outcome of this is this article in this magazine that is lying here around. You can also read it online. And as I said, basically, you have here these 3 experts in tailored waveforms, Erwin Kessels, Johann Schulze, Martin Kuba, who in this kind of article tell you why tailored waveforms are awesome and why simulations can help with understanding these discharges. Now, to get to the simulation, you basically have seen this before. James has already shown the sketch of the reactor we're simulating. So it is CCP to PD100 to maybe a few thousand volts. Pressure range overall is some millitorr to some few tens of millitorr, where of course at the lower range we are kind of at the edge of what fluid models can do. And maybe I will get back later to this. Then if you do a conventional RF bias, you have some hundreds of watt at 13.56 megahertz. And then the tailored waveform biasing, where we are using an IE last form, which I'm going to show at 400 kilohertz, and it's just argon. Just as I said, one block that we hit is we had no idea how these waveforms that come out of the generator actually look like. So we first did some kind of sanity checks. Where we just see, can we actually in general simulate the effect of the charging of both the blocking capacitor and the wafer. So in one point we do not have a wafer in the chamber, but we kind of fiddled a bit with the HPAM settings, and then you can actually, with some maybe cheating, realize a time-dependent voltage on the capacitor. As long as you have set voltages, it doesn't work for set powers, but you can actually get there. And the other one, we have a wafer, but there we kind of say we keep the DC self-bias constant, just to check whether we can separate these, simulate the effects separately. Now you see a picture of the idealized tailored waveform we used. This is basically, I mean, when you look at kind of, for example, at the people who sell the generators, they have their little articles, blog entries, where they explain how it works. And this is basically this idealized waveform they show. Said we have a short positive phase, then transition to 0, and then this long negative phase with the slope, and then it goes back up to the positive phase. And yes, you see just some values which we used for this test B, where we have the wafer, but a constant DC self-bias. Without the wafer, but with a time-varying DC self-bias, we basically just checked with slope, and again without with slope and without the slope. And in general, we can get these non-energetic IEDFs using these tailored waveforms. One thing I'd like to show you is that in general, we also see a low energy peak at maybe roughly a few EV to maybe a few tens of EV, depending on your applied voltage. However, when you look at, and you don't see this experimentally, however, when you look at this distribution function, also it's a function of the angle, we see only this one peak, which we see experimentally, which basically tells us that this low energy peak consists of ions which are spread over a pretty wide angle. And one question is, which we couldn't so far answer, is where do these ions in the simulation come from? We don't know yet. What we also don't know, are these ions actually real and just don't show up in the experiments? Because measuring ions spread over wide angle at low energies. This can be missed by your instruments, or is it an artifact in the simulation? We simply don't know right now. I just wanted to point out that I'm going to show some ideas later that we in general see this additional low energy peak you do not see in the experiment, but we don't know where it's coming from right now. So if you do this, so yeah, we kind of set this up that we kind of have this time varying DC self-bias on the capacitor. And then as I said, we just ran it without a slope and with a slope and with different capacitances of the blocking capacitor. And if we have a rather high capacitance, I think this was something like 1 microfarad, which is way larger than you usually have. But the nice thing about simulations, you can just do the stuff and see what happens. And we see we have this time varying DC self-bias, but it varies only very slightly. It varies only by 1 or 2 volts since the capacitance is so large. And we do see if we do not have a slope, we do actually get this more energetic ion peak because there is nothing to compensate. We have no wafer that is charging, and the DC self-bias also doesn't change a lot. If we now have the slope, again, DC self-bias is basically the same, just now with the slope. DC self-bias changes only slightly, but while we have this correction slope, but there's nothing to correct for, so we get this wider peak. If we now decrease the capacitance of the blackened capacitor, again, I have no slope. Now the DC self-bias changes a lot more, roughly by 20 volts. And in this case, no slope. We now have something to compensate, but we don't compensate. So we get a rather broad peak. If we now apply the slope, we get again the sharp peak. So we can say, yes, we can, in general, simulate this charging effect of the blocking capacitor and get reasonable results. Now, if we apply now the wafer, as I said, now we have a constant DC self-bias, and basically we played with the voltage waveform itself with some other materials like the wafer properties. One thing we change, for example, is the dielectric constant of the wafer. We see if we have a rather high 10, we do get a pretty sharp peak. Maybe we overcompensated it, so we have a kind of a bit pronounced high energy tail here, but it is pretty sharp. If we now decrease the dielectric constant, basically this kind of decreases the capacitance of the wafer, which gives you a higher voltage drop over the wafer at the same charge. And we see if we, so dielectric constant smaller, voltage drop over the wafer is larger, and we see we still get a pretty sharp peak, but now we have a kind of undercompensate, so we have this kind of flank for lower energies. However, what we also see, the peak position does not change. Peak position is pretty much the same. Only if we kind of get to, if the dielectric constant becomes so small that the slope can keep up with the voltage of the wafer, we see basically this peak vanishes. But in general, the dielectric constant of the wafer, unless you get into this regime, dielectric constant of the wafer or capacitance of the wafer does not change the position of the peak, just the shape of the peak. We also looked at how does the ICP power change it, and again, upper left is the same as before. See, higher power means higher density, higher currents means wafer charges faster, and we see that here. If we lower the power to 250 watts, smaller currents, we now undercompensate because it doesn't charge as fast as before. If we increase the power, we kind of start to undercompensate because it charges faster. So it looks all good. One thing two things I still like to show is if we change now the slope finish, so we keep the same waveform, same amplitude of the positive phase, we go to 0, but when we change the voltage where the slope finishes. Again, this has now an effect on the shape. We see the smaller this finish, the smaller the slope, and the more we undercompensate. But again, it does not really change the position of the peak unless you get to such a small slope that you don't compensate at all and the peak vanishes. And again, we have seen basically wafer properties, ICP power, slope has an impact on the shape of the peak, but not on the position of the peak. What does actually have an impact on the position of the peak is the amplitude of the positive phase. Again, here we just changed the amplitude of the positive phase, and you see it doesn't really impact the shape of the peak, but it does change the position, and this is basically just higher, larger amplitude means you get a more negative DC self-bias. And this gives you these higher energies, but it doesn't change the peak. We did some others, but I don't want to bore you with too many similar slides. But just what we've basically seen in this simply sanity checks is the P position is mainly determined by the voltage on the blocking capacitor, so the DC self-bias, which is mostly given by the amplitude of the positive phase and what I have not implicitly shown, the voltage at the beginning of the slope. The peak shape is mainly determined by the slope in the negative phase, wafer properties, the charging speed of the blocking capacitor, and the plasma density, or rather the current to the wafer electrode. So kind of have these two different characteristics which influence the IDF in different ways. And this is basically, I think, a nice outcome of the simulation, that you can actually see which part of the voltage waveform has actually which effect. And yeah, then we went on and said, okay, let's compare to experimental IDFs. And as I said, one issue that we shaped is we have no idea how these waveforms look like. And when we asked Ben Harris and Daryl Wright at ORFAT, who did actually the experiments, how do you actually kind of define your waveform at the generator? They say, yeah, we have a button where we set the voltage. So, yeah, but which voltage? I don't know, it's just a voltage. And okay, luckily they were so nice and put a voltage probe in the generator, so they actually measured the signal that comes out of the RF generator. And you see in green, this is the original averaged over hundreds of cycles. And you see it's actually not as perfect as we assumed. It's not that far away. And I think the major difference is that the positive phase isn't constant, but this was more shape kind of bits like of a sinusoidal half cycle of a sine. But we did approximate again with this kind of simplified shape where we kind of define these 5 points. So another challenge is then the wafer itself, because they did the measurements with an SiO2 wafer. And as you know, SiO2 wafer does not mean that you have a solid SiO2 wafer. It means that you have a silicon wafer with thin silicon oxide layers. And how do you simulate this? I mean, you can, of course, you could have maybe say, okay, we actually going to resolve that stuff, but this means you would need to have micrometer resolution in your mesh, which you don't want to have. But what you do basically do in QVT or the HPEM is that you say this material is a wafer, and then you can set its thickness, its dielectric constant, and its conductivity. And how do you do this with this stuff? Fortunately, conductivity is not that much of an issue. I haven't explicitly shown this, but what you see at conductivity, as soon as it becomes sufficiently small, it doesn't do anything. So it's, as long as it's sufficiently insulating, you can change the conductivity by orders of magnitude, nothing changes. And this, of course, nice because silicon dioxide is highly non-conductive. Even if it's just 1 micrometer, this basically dominates the resistance. So we can basically just say, okay, we just set the conductivity so small that we get this insulating effect and we don't need to care much about this. Another thing is the work of dielectric constant. What we did here is basically that we assumed this to be a kind of series of capacitances. And in a series of capacitances, the dominant one is the smallest capacitance, which in this case, since it's so thick, would be the silicon. So we roughly said we approximate this then using low conductivity. So we have the insulating of the effect of the oxide, but then use the dielectric constant of the silicon. And how did that turn out? Not too bad. Basically, what you see here, we have in blue the measured IDFs, and some points you see 2 peaks. This is actually an effect of averaging over lots of different traces. So when you look at a single trace, you only get 1 peak, but maybe to some jitter or something, you maybe have a switch between 2 different peaks here sometimes. And in orange, you see our simulated IDFs, again with this low energy peak. And what we see is we actually hit the position of the peak very well. There's basically maybe just a few EV differences, but this is a very good fit, I would say, when it comes to position of the peak. We see that the shape is a bit different. In general, we see in the simulation is that we overcompensate a bit, meaning that we have that we don't get kind of these really sharp peaks, but we have this high energy tail. But again, we had to make a lot of assumptions about the wafer, about the blocking capacitor, and basically what it tells us, something does not charge fast enough. That's true. Therefore, the blocking capacitor, of course, you can also have stray capacitors, which can have an influence. So we did a bit of checked what, I mean, because these results, these are good. You can say, okay, like basically this tells you, you could use this, for example, to say how large do I need to set, for example, the voltage amplitude of the positive phase to get a specific energy. but not about the shape. Because one thing we kind of wanted to find out what we're looking into, even if we don't get perfect agreement, it's still nice to know what actually causes the difference. Why do we see a difference? So one thing is we first checked again the DC self-bias calculation. So we went with a constant DC self-bias and then some different treatments of how the capacitors charge. So in the end, what you need is the current flowing to the capacitor. And in HPM, you can, for example, take different surfaces into account. You can take only conduction current or also displacement current into account. So we went through these different options to see how it changes. And what you basically see is that this basically, again, leads more rather to a shift in the P position rather than in the shape. So it seems to be that it's probably rather the wafer charging where you're looking at. Another thing we looked at is the measurements were taken at 1.6 milliliter, which is very low for fluid models. So we actually ran it with a simplified model because at these low pressures, you can easily get, or more easily get, instabilities. To prevent this, we ran a simplified model. For example, one thing that in my experience can go a bit haywire is at these low pressures is gas heating. So we turned this off and just ran at a constant gas temperature. And then what we did so far, or that is simply to check how does the gas temperature actually impact the IDF. And again, we see it's reached rather to a shift of the ion energy distribution functions rather than a change in the shape. So we're still maybe looking at some other model choice we want to go through, maybe approximate the waveform a bit better. And one thing I would like to mention is when we set up a top of this wafer, there's also a voltage probe and the retarding field energy analyzer. Because the question is, does this actually impact the charging of the wafer or the blocking capacitor, which we do not get in the simulation. So maybe to summarize, as what we did, we kind of, together with Oxford Instruments, tried how well can we simulate these tailored waveforms and resulting EDFs. And what we've seen, we can very well replicate actually the peak positions, but the shapes are a bit off. We see some overcompensation and currently changes that the wafer charges a bit slower than in actually the experiments. And so we still want to maybe check the influence of some model choice, model influences, the influence of some model choices, and maybe see if we can maybe clarify the influence, for example, on all the measurements stuff that is on the wafer. I think overall this was a successful successful project. If you have any more information about how you can simulate these tailored waveforms, please email us at info@quantemol.com. And again, if you want to read more on why tailored waveforms are awesome and why simulations are awesome, you can read the article in the magazine or on our website. And thank you.